Is that everybody on? Go ahead.
Are both labs due Thursday then?
Both labs from my class will be due Thursday's fine. Yes.
Okay.
Sorry, could you repeat when the lab exam is?
Thursday next week.
Oh, it's Thursday next week.
Yes. That's the lab
Not
exam.
this Thursday. the
Thursday next week.
Yeah, got it.
Yep. Okay. Is that okay? Anybody else?
Which ones does it cover?
Whatever we've done that we
Okay.
haven't been tested on yet. Right, so that does nothing that,
So we have no more labs.
no more labs.
Sounds good.
Cool.
Got it. Everything.
Yep, all the labs will be lectures from here on out. Go ahead, Peter.
When's our lab final?
Thursday,
That's Thursday.
next week is the lab final. It'll be only on the labs that you did. Will not be on any labs that you did not do, even though it was,
Schedule.
the idea was going to be we were gonna do them this week, next week, whatever else. Those will not be on. Okay. Is that okay? Okay, let's get started. Chapter 9. Where did we leave off? What were we talking about?
Structure?
Lewis structure. So this is chapter 9. Chapter 9 deals with what? What's the topic of chapter 9? What is it? Chemical bonding.
Give the answer.
That deals with ionic bonds, covalent bonds. We talked about metallic bonding, right? Metals next to metals. We discussed the Haber cycle, where we saw that you get a lot of energy by combining things. That's called what? Lattice energy. Thank you. Absolutely. So we covered that, right? If you recall, this is last Tuesday, a week ago. Then we progressed into Lewis dot structures, right? Where we just simply looked at the Lewis structure and you put dots around it and doubled them up based on their valence electrons, right? Okay. So from there, I think we did that with things that metals and nonmetals, and we saw what it looked like forming ionic bonding patterns. Remember, ionic bonds would be metal and
Non-metal.
nonmetal. Covalent bonds would be
Non-metal and non-metal.
nonmetal and nonmetal. Is there a polar covalent versus a nonpolar covalent?
Yes.
Yes. What's the difference?
The polar covalent are actually repelling each other, or the electron itself?
Polar covalent means that the electrons in the bond are shared
Correct.
unequally.
Equally.
Yeah.
Nonpolar means they're shared equally.
Correct.
Okay. Based on electron negativity, which
Yeah.
is, these are all terms that you should have known
Yeah.
from 65, right?
Yeah.
Mhm.
Okay, so based on electron negativity difference, will
Correct.
determine whether or not it's polar or nonpolar covalent,
Correct.
or whether or not it's ionic.
Yes.
Okay, and we'll talk, I think, a little bit more about that. So I'm going to keep it relatively light, and we're covering mostly stuff that we already know.
Awesome.
So that way it's not overstressed from taking the exam earlier or taking it later, but you still need to recall these things, they're still important. And I might touch on a couple new things that I'll point out as we get to. What do we have here? Okay, here's an example of H2O Lewis structure. I'm gonna skip through this, knowing you guys know Lewis structures, and then we'll do a couple Lewis structures from scratch, so that you can recall exactly how that works. Okay. Just to recall, this is in terms of a Lewis structure, you have the H2O here, and this is called the center atom between these three. The electrons here and here could also be a dash, and that means they're shared. The electrons that are sitting by themselves are called lone pairs, and they're only associated with the atom that they're touching or next to. Okay, so this is a lone pair connected only to the oxygen. This is a lone pair connected only to an oxygen, which another term for that is called non-bonding pairs. They're pairs, but it's not bound, non-bonding. Bonded pairs are these here that are shared between the hydrogen and the oxygen, just to recall that. Okay, you could also see these with lines. The lone pairs are never with lines, they're just with the dots indicating that they're by themselves, and they're connected to whatever they're touching. The lines are the same thing as the two dots that mean that it's a bonded pair. Okay, so non-bonded versus bonded. Okay, another representation of that.
So in that.
And another representation. And once again, we're just going to do one of these. These are the same kinds of things here. This is just showing you, we're going to do a whole, the whole
Shebang.
Lewis structure. So I'm not going to worry about this here. This is sort of like before we do the whole thing, but you guys already know how to do it. So
Yeah.
I think this is more than what's necessary here. Okay, before we start that though, let's do a brief reminder about electron negativity and bond polarity, which we kind of already did, right? So, let me see here. Electron negativity and bond polarity. Looking at the periodic table over here, electron negativity is in reference to each atom and the pull that they have for an electron to come to them. Okay? So that means that as I go from the metals to the non-metals, would the electron negativity increase or decrease in Y?
Increase.
Increase.
Right.
Simple the 8.
Because they have, non-metals like to do what? Share or gain electrons.
Gain, yeah.
Non-metals like to
Give away.
donate. And we know that because they want to look like either, if you're a metal, you want to look like the previous noble gas in terms of your electron configuration, you're more stable, okay? If you're a metal, you want to look like the next noble gas. And that's because, once again, your electron configuration makes you more stable,
Right.
Which is the foundation for covalent and ionic bonding.
How-
So that's what electron negativity represents.
Plus.
That is fairly close to the affinity, right?
Electron affinity, similar idea, absolutely.
Okay.
Absolutely.
Yeah.
Bond
Oh,
polarity
you
now
wanna ask
deals
about
with
that in
two
front
things
of
and the
us,
bond
like-
between them, and how polar that bond is. So if it's an ionic bond, you presumably have an electron that's transferred from one thing to another, and you have a distribution of a positive and a negative charge on each side. That charge difference is bond polarity.
Yeah.
The closer to where they're shared and there's less difference in charge from one side to the other is the lower bond polarity or least bond polarity. In fact, it's usually called non-polar covalent if they're completely shared or equally shared. So that's the distinction between electron negativity is per atom and the bond polarity is the bond between two atoms. Okay? Once again, electron negativity is the greater the electron negativity, the greater the pull you have for an electron to come to you from the nucleus.
Yeah.
The more bond polarity you have, the greater distribution in that bond of the electrons favoring one atom over the other. That's it. Okay? And that should be a review. One way to represent this, so if I have something like hydrofluoric acid, I have two representations here. In fact, let me write up the different things that are possible. Let me do this. If I have sodium plus ion, chloride minus ion, and a bond there, this is the most polar, so this is ionic, and very, say, polar. Okay? Just to make sure that these ideas stay. This is an ionic bond. If I look at HCl, I have a polar covalent bond, and this is just polar. Not very polar, polar. Here the electrons are favoring the chlorine. So here you have a complete transfer. The electron that was here was transferred to here and is represented in the charge. Here, there's no charge on either one, so we could say the electrons are unequally shared and favor the thing that has the higher electron negativity. And in that context, I would say that this is a partial negative and this is a partial positive.
Yeah.
Go ahead.
So ionic is basically like a complete transfer?
Presumably, yes. I'll
Okay.
talk more about what that means later, but for now, yes.
Okay.
Right? And
Still
here,
sharing it.
this is a polar covalent, polar. This is an ionic, which is very polar. This is much more polar than this. These are complete charge distribution versus this. And polarity means if I look at this side and this side, I have a different in charge distribution. When I have two atoms, that's based only on the bond between them, because these electrons are dictating where that charge distribution is. Okay. And lastly, I have something like this, where I could have Cl and Cl. Now here, These have the same electron negativity, so the electrons that are in between that are being shared are being equally shared, and I'll represent them right in the middle. So in this case, this is called a non-polar covalent bond. And this is obviously non-polar, I don't need to write it. Does that make sense? So these are the three levels of bonding types in the context of polarity. Non-polar, because these are the same electron negativity atoms and they're sharing the electrons. Here, equally, here I have two different electron negativities for two different atoms. They're not complete distribution of one electron going somewhere else, but or two or whatever. Here the electrons are still being shared, but they're being unequally shared where they're favoring the chlorine. Higher electron negativity, partial negative, partial positive, polar covalent. And here I have a complete charge distribution where I have the electron leaving the sodium, going to the chloride, represented by the ions. This is ionic and the most polar. And these are the things that we're discussing in terms of electron negativity and polar bond polarity.
Got it.
Is that okay?
Yeah.
Is that breakdown? Okay. Now, another way, so here and here, so here, this is non-polar, so there's no polarity here. But here, you could represent this with what's called a dipole moment. And I could draw an arrow towards the negative side,
Yeah.
and I cross the back half, meaning this is the positive side, that's the negative side. And that's what you see here. It's a representation called a dipole moment.
Quick question about that. Are those only done on partial polar, or can they be done on the very polar, like ionic bonds?
Same thing here, even though this one is really obvious, this one is not. So this can be used to exchange this representation. This is already known.
Got it. Okay.
So usually you'll see it here.
Okay.
The other thing about this is I could also do this to something bigger than two atoms. In that case, it doesn't just go by the bond. It now goes by the structure. So if you recall VSEPR, valence shell electron pair repulsion, you put together the molecule when you have more than two atoms based on the Lewis structures, where I take the center atom, I build a skeleton around it, I then fix the number of bonds that go into it, and then I look to see whether that molecule's polar or not by looking at one side versus another. So it's not based solely on the bond, it's based on the structure. And the VSEPR just means that each atom around the center atom tries to get as far apart from each other as possible. Valence shell electron pair repulsion, they're trying to get as far away as possible. So these are the three simple cases here, and this is one representation. I think we'll talk a little bit more about dipole moment and what that means. But you can imagine that means the magnitude of the charge relative to the distance of the atoms, right? Something similar to Coulomb's law.
That's what I was going to ask you, just the charge and the distance.
That's how you come up with the dipole moment in terms of a quantitative analysis of it. And it comes out in coulombs, which you can convert to what they usually use as Debye's. And that would be the unit use, which is kind of a simplistic system. Will be like 1, 2, 3, or 4. That would be considered polar versus, or what level of polarity from a quantitative perspective. We won't go too deep into that here.
That doesn't sound like something like
So this is that, okay.
that. You're not missing anything.
Okay.
Okay, this is just electron negativity. I will point out Linus Pauling is the one that came up with that electron negativity chart. Linus, he did this down the street, not too far from here at Caltech.
Really?
Oh,
So yeah,
Linus.
so he was one of at the time he was living, he's probably the most famous scientist at that time.
Didn't you win the
Nobel Prize?
2 Nobel Prizes, right? No?
That I don't know.
Oh.
I know I'm pretty sure he won one. I know one of the faculty I had at UCLA shared stories about him when he was also a faculty there. David Eisenberg was one of the more famous X-ray crystallographers in the world. So there was a big group of scientists that were pretty prominent back, I'd say in the 80s, maybe 70s, and that was at Caltech, and that's where a lot of that work was done. One other thing I'll point out is the electron negativity. How was it determined? It was based on taking atoms that were the same, that were connected. So in this case, I'm just calling them here diatomic, heteronuclear, so they're the same. Two different ones, and then how much energy it takes to separate them. That was how the electron negativity distribution was determined. Right. Okay, so just to remind you, electron negativity, if I start down here, cesium and francium are the lowest, and fluorine is the highest. And so it goes, primarily will go this direction, diagonally up, will be increasing electron negativity. Okay. Then you can see this is an electron negativity chart. So here are the electron negativities. The higher it gets, the more pull you have for electrons to come to you. And that matters in a bond.
Right.
Okay. Why wouldn't helium, huh?
How do they calculate?
The bond energies. That's what I just talked about on the last slide. Right? The heteronuclear diatomic bond energies, how much energy it takes to break that bond.
Correct.
Why does he have to do this for me?
Helium, xenon, argon, why are those not included here? They're really stable, right? So they don't really have an electron negativity. It also, so there's no reason for them to be pulling something next to it because they're not going to form a compound. Right? They're already really stable.
Are we talking about noble gases?
The top three, yes.
Oh.
Some of the ones down here do have an affinity because they can form, and you happen to notice where they are too, right? They're where you have d orbitals. So there are other things that can go on where they can interact, right? And we'll talk a little bit more about that later, about some of the oddities of that.
You should tell him what you didn't know about the orbitals.
Okay, so simple trend, electron negativity increases across the periodic table and decreases going down. Same way, you just know that diagonal. That's the main thing. So two things. One is if I give you something where I need you to figure out an actual number, I'll provide you the table. That one we just saw. I'm not going to make you memorize or use your notes for this. You'll have that. But I could say, I could ask you to compare some things or multiple choice questions, and if you know that there's a diagonal that goes up this way,
Right.
then you know the increasing electron negativity.
If you give
So
us
then
two
you would have,
elements.
yeah, so if I have something like, what's more electron negative, sodium, magnesium,
Isn't it kind of
silicon, or chlorine?
Similar.
Everybody should automatically know it would be chlorine in that set.
Which is actually what leads to that.
Okay, so you would know, you can know patterns without knowing the numbers.
Exactly.
Yes.
But if I ask for a specific number, then I have to give you the charts.
So upper right is the strongest, basically.
Just like this. You see
Yeah.
where it says increasing?
So helium would be like,
Oh, fluorine.
Helium's not part of
A
it.
part of it.
I mean,
Fluorine is the highest one you could have. It's about 4. These are the weakest ones, which are CS and francium, which are about
Don't
0.7,
forget
0.8.
the picture that we were talking about.
So it goes
the
up this way.
increasing
And that's all you really
The
need to know about
size.
this.
of
Okay?
Picture I found on Google.
Okay. So once again, this is just still a review,
The periodic trends.
and this shows some of those trends that I just talked about.
Why? It's fine.
Okay, I guess, I don't know how much this will help, quite honestly. You already know certain trends, and you should, but this is saying electron negativity is inversely proportional to atomic size. That makes sense.
Yep.
But it's not something you really need to know. You already know the individual trends, so it's not that, there's nothing added to that statement. And here. So when you're looking at a chemical bond, you're looking at the difference between the electron negativities of each one of those atoms that are part of that bond. The difference is represented by this delta for the change, and the capital EN is the change in electron negativity. So if I look, for example, at hydrogen and fluorine, let's say fluorine was 4 and hydrogen's 2.1, the difference there is what? 4 minus 2.1. Doesn't matter which one's greater or smaller, it's just the greater one minus the smaller one, that's the difference. It's not asking for a plus or minus, it's not directional. It's just the difference in the electron negativity. The degree of that difference will dictate whether or not you have one of these three things here. So if the change in electron negativity is 0, you have this scenario right here.
Right.
Yeah.
If the change is
Non-polar.
usually between 0.3 and 1.7, you have this one.
Right.
And if it's above 1.7, you have this one.
Yes.
Now, there are various charts on how that works.
Yeah.
Different charts will depend on different things, and that's based on lab. So some people will say, well, 1.9 and above is this, and under 1.9 is not.
In 65, you gave us which one to follow?
I'm going to give you one to follow here. I think it's the 1.3 to 1.7, I think is what I gave you, right?
Okay.
And you'll do the same thing here, so I won't change that. I just want you to be aware that there are other potential charts.
Right.
And the reason for that is because, let's say I have hydrofluoric acid, that's 1.9, which we just did, the HF.
Yeah.
1.9, if you put that into water, does it separate into ions?
Yes. Oh,
It's a weak acid, not a
Right.
strong acid, so it
Right,
doesn't
right.
separate that much. The idea is if it's an ionic compound, you put it in water, what happens?
it ionizes.
It ionizes.
Right.
So under that concept, 1.9 and above would be ionic.
Sure.
But the reason for that is not because it doesn't ionize, because it's not strong enough to. It develops, if you recall, hydrogen bonding within itself, its own intermolecular interaction. So when I put that in water, the water has a hard time breaking those hydrogen bonds between the HFs and the other HFs.
That could be going back and forth, back and forth.
It will form an equilibrium.
It could,
But it's harder to break apart than, say, HCl. So if you recall, why does something form hydrogen bonding? Did we do that?
yeah,
You
it
did,
was
right?
with the lab where we created the bases and the acids, but
Anything where I have hydrogen.
uh-huh.
So intermolecular forces, there are basically three of them that you'll learn at this level, right? You have, what are they called then? Van der Waals are the first two. London forces or dispersion forces are one. This is the general temporary dipole moments of things that are connected or next to each other. And as one changes, it bumps into another one, it flips it, changes it, makes it a little more polar, bumps into the next one, etc. That's a temporary dipole. Then you have the dipole, another Van der Waals, which are the permanent dipoles, so they align according to that, right? And then you have the hydrogen bonding. And that has a hydrogen involved, top there, and it has one of these small, highly electronegative atoms connected. It's got to be small. So it's got to be either NO or F. When NO or F bind to hydrogen, then what they do is they're actually, it's not a chemical bond, it's an intermolecular bond. Let me see. This okay now?
Yeah.
I'm going to have something like this, a water, and I have two lone pairs there, and I have here another water. Okay, and what happens in this kind of scenario, small electron negative atom, either oxygen, fluorine, or nitrogen, and hydrogen. These things here are bonded. Is the oxygen or the hydrogen have a higher electron negativity? Oxygen. So the electrons in this bond are closer to the oxygen, right?
Yeah.
So I could also do this kind of thing and say that's a partial negative, this is a partial positive.
Right.
How many electrons are in that hydrogen now?
None,
Basically zero,
right? It's giving up.
right?
Yeah.
I mean, the one here, it's in a bond, but it's a loose, these are favoring the oxygen, so it basically has no other electrons.
Right.
So guess what? These two here can take advantage of that, and they form this hydrogen bonding pattern between the
Yeah.
H2Os.
I remember that.
Okay? And that's how that works. But that's also why this has to be a small electron negative, because it has to have the extra lone pair, so it could be a nitrogen or a fluorine. So then the HF forms their own hydrogen bonding patterns, as I was describing, and that's harder to break apart. And so these are the different types of intermolecular interactions, which is chapter 11, by the way, that I'm going to probably skip for this class, which I skipped last year anyway. So it's there. I might throw in just enough that makes it basic for your understanding, but I think we covered it in 65.
Yeah.
Okay. So this is the term change in electron negativity that we were interested in here.
That's not here.
Okay. Dipole moment was the arrow that I talked about. It's also given by mu, and that's this right here.
Dipole.
I'll talk a little bit more about that later and what that means, but I already mentioned it's the charge of something multiplied by the distance, okay, of two things that are close to each other.
Why do I remember
Mhm.
It sounds so familiar.
So here, and this is somewhat of a review, which is kind of why I'm moving through this fast, and I chose this time to do it, since I know there are tests,
Yeah.
this wasn't part, that's kind of, I tried to fit this. So the greater the change in electron negativity for the bond, the larger the dipole moment, the more polar the bond. Those things always stay in sequence, you can't go out of that sequence. You go backwards from this, you could say the lower the change in electron negativity, the smaller the dipole moment, the less polar or the more non-polar the bond
Can
is
you
another way.
remind me what the dipole moment is? I'm trying to remember.
That's what we just
Oh,
did.
it's just, okay, it's
That's
just
the-
that, yeah, okay, got it.
That's,
I was like, I know, sorry, I can have a brain fart. It's okay. No, it's fine, I remember that,
You okay?
yeah. I just didn't connect that that's what it was called.
Okay, so
I'm
Okay, so
sorry.
here's what we're looking at now. This is very, I guess this is different. So I'm giving you a different table. Thought I was giving you the same table. This is your book now. And the electron negativity difference between, says covalent, that really should say non-polar covalent, like I had it written on the board. So non-polar covalent is the electron change in electron negativity or electron negativity difference is 0 to 0.4. Polar covalent is going to be 0.4 to 2, and 2 and above is ionic. That's your new scale.
Okay.
That's it. The old scale was 0 to 0.3, 0.3 to 1.7. So the 0.3 now changes to 0.4, and the 1.7 changes to 2.0 for the exact same reason I just mentioned, probably the HF.
Right.
They want to say that that is not ionic because it doesn't separate into ions. Even though other things that are lower than that will separate into ions. So it's all relative to the scale that that you're looking at. Change electron negativity increases going down, polarity increases going down, these things here. And once again, just a review. Same kind of thing here. So here's this chart, goes from 0 to 0.4, 0.4 to 2. This is the essentially equally shared electrons, nonpolar. Electrons shared unequally between here, and electrons completely transferred between there. Once again, we stopped at 1.7 in the past because 1.7 was an indicator that the percent ionic character, which is another term that I'll bring up later in this chapter, was over 50%. So sometimes they say over 50% ionic character is an ionic bond. That usually occurs at about 1.6 to 1.7 in terms of the change in electron negativity.
Quick question, if your electronegativity difference lands right on 0.4 or right on 2.0, do you say both or do you choose one? Is there one that you should lean towards?
On a multiple choice, give the best answer that's given in the A, B, C, D.
Okay.
On a problem that you solve, just state why you did whichever you do.
Okay.
And that's good enough. Because there really is no necessarily right answer unless I define one, and I'd rather leave it open.
Okay.
So that if you got a 0.4, you said, this could be this or this, I'll choose this.
Okay.
That's good enough. That shows your recognition of it. And if you just happen to choose one over the other, I probably won't say anything. If you choose something way over here for the 0.4, then it's obviously wrong.
What
Right.
was your question?
If it's right on 0.4 or 2.0,
Yeah.
which one is it?
It's like on the board
Right. And why do I say it's open? Because they're different. What about the 0.3 to the 1.7?
Yeah.
Okay.
Right.
3.
So you could.
Okay.
So when the 0.3 one here, then you would say it's this one, and the 1.7, then this one would be this
On that
side.
side, right.
Yeah, if I put it 2.1
Yeah,
it's on this side, I want to leave it a little bit open like that.
Sounds good.
So the polarity of the bond increases going this way. And by the way, here's your partial, and then there's your complete. Just one other thing I want to point out here. When I'm looking at this here, and I'm looking at 0 to 0.4, so now if I have a diatomic in its elemental state, so that would be what, F2, Cl2, Br2,
Yeah.
I2, remember all of those
Yes.
diatomics?
The 7?
Better.
There clearly is a bond or bonds between them.
Yeah.
Right.
What would those be in terms of the change in electron negativity and the polarity?
I have to assume equally shared.
0? Yeah.
It'd be
Zero,
what?
yeah.
Zero. Change
Zero.
electron negativity would be zero.
Correct.
Those are really obvious that they fit in here.
Yeah.
They're equally shared. The same electron negativity, both, right?
Yeah.
But that doesn't mean that you can't have something that is also, that fits in here that are not the same.
Yeah.
Right.
But you would have to know what the electron negativities are and make that determination.
Correct.
Otherwise, you would assume that with different atoms that are non-metals, that you're going to have a change in electron negativity most likely greater than 0.4. There are a couple where you don't, but you'd have to have the numbers to know that. I wouldn't expect you to memorize that. Okay, so I could say though, I mean, one of the things that, so the trends of electron negativity, we said increases going from left to right. Also increases going from the bottom up,
Yeah.
right? So then if I looked at O and Cl, which one would have a greater electron negativity? One's more to the right, one's more up on the chart. That might be hard to determine that, right? And most likely that might be one that fits within here. Just intuitively without knowing the numbers. Does that make sense?
Right.
But other than that, you can't really determine. I mean, it's pretty straightforward that the F and the O, they're significantly different, but they might be close enough. They could be around that area. But less likely, the O and the Cl, the N in the Cl, or the N in the Br, who knows how close those can be. Those would be where you get them in here, even though they're different elements. Okay? To give you a sense of, okay, so here's the dipole moment, the magnitude is right here. So this is the mu, that's the dipole, and this is QR. And Q really represents the charge, okay, of, in this case, we're going to look at the charge of, say, an electron, or the charge of, say, a proton, or something like that. And we're going to look at that in the distance it has relative to whatever it is you're comparing it to. That's what it is. So usually that's a very small number if you're talking about one thing. So you'd have something like the Q is 1.6 times 10 to the minus 18 for like an electron kind of thing. Then you multiply that by the distance. That's usually going to be given in, and this is important, it's kind of given, it's usually given in something called coulombs. Okay, so for Coulomb. So he came up with his own system, and if you take the Coulomb times the distance in meter, you end up with, and you do a conversion factor, you get this thing called D, which is called a debye. Those are the units associated with these. I'm not going to be that strict with this. I'm not going to test you on it. Just want to give you a sense of what it is. Okay, so mu is the dipole moment given in these easier numbers here. The greater the dipole moment, the greater the change in electron negativity, the more polar it is. Okay, so these patterns here, change electron negativity 0, there's 0 dipole moment. That should make sense. Here I have chlorine and fluorine. I have a 1.0 change in electron negativity, and my dipole moment is 0.88. And so you can see how they're very close to each other. Here it gets a little greater between the metal and the non-metal, lithium and fluoride. I have a 3.0 change in electron negativity, but a 6.33 dipole moment. Which is, once again, that D's for, not for dipole moment, that D's for debye. Okay, which is essentially a conversion from a Coulomb and multiplied by a distance, usually a meter. Okay. Now percent ionic character. So once again, the old chart that I gave and that I referenced before was where the percent ionic character above 50 is generally thought of as something that's now an ionic bond. That's what this is referencing. So when the change in electron negativity is somewhere between 1.6 and 1.7, somewhere in that range, you now have 50% of that bond is considered ionic character, transferred of the electron from one thing to another.
Between
50%. So
1.6
over 50% is considered in the 1.7 chart an ionic bond. We just modified that to a new chart where we said 2.0. So that means I'm well above 50% ionic character before I'm calling it an ionic bond. And what I have here is that I have the percent ionic character relative to the electron negativity difference. usually you're gonna take a chart like this, you go across the 50% ionic character, and anything above it, this is where the LiI, LiCl, etc. Anything above this would be considered an ionic bond. If you didn't have the electron negativities and determine the change, the difference in the electron negativities. And then anything below this, these would be considered non-ionic.
Right.
Okay, they're below this is below 25, this is probably somewhere around, this is over here close to 0. I would say, what would that be? Probably non-polar.
Right.
Covalent, maybe here's a polar covalent, definitely a polar covalent. In our new chart, maybe these are polar covalent and everything up here are ionic. You draw like a little graph going between there and you could go off of where that is relative.
Okay.
Okay, the main thing is looking at the chart and understanding that these are percent ionic character is relative to the electron negativity difference. And that's also usually looking at the ionic character of diatomic molecules in the gas phase, because if they're not in the gas phase, you can't really determine that much because you can't separate them. You can't sit there and take two atoms in a solid and just break them apart and see what their bond energies are, right?
Yeah.
The energy it takes to break them. So they have to be in the gas phase. Okay. Just to make sure I want to make this clear, the change in electron negativity, as that increases, I increase the ionic character.
Right.
Okay? And you see that as I go this way, I go this way. Increase in electron negativity difference, this is the difference. I increase the percent ionic character. That's the correlation.
Increase.
Okay, good. Okay, so now we're getting into writing Lewis structures. This is good. We're moving at the pace I want in this area here. I'm gonna let you read that. We've done this before. I want to just do a couple.
Awesome.
Okay?
Yeah.
And then all of those words should be correlated to what we do in making them.
Yeah.
So write the Lewis structure for H2CO. The very first thing you're going to do is you're going to do how many valence electrons do I have to work with? Okay? So how many valence electrons do I have for H2CO?
7 plus 2, 9.
How many do I have from the
H2CO?
oxygen?
That would be 6.
6. How many from the C?
11.
4.
4.
Okay, for those of you that are saying them out loud and those of you that are not, I want to make sure everybody understands. The group number is the number of valence electrons.
Right.
Yes.
Oxygen is in group 6. It has 6 valence electrons. It's that simple.
Correct.
Carbon is in group 4. It has 4 valence electrons.
Yes.
Hydrogen's in group 1. It has one valence electron. So that's 6
11.
plus 4 plus 2.
Yes.
Right. 11. Oh, 6 plus 4 plus 2.
6 plus 4 plus 2.
Yeah.
1 for each
Oh, hydrogen.
hydrogen.
Yeah.
That's total of
12.
12. If I ever had an odd one, that's a problem, right?
Yeah.
Because I wouldn't have pairing of the
Correct.
electrons.
Correct.
Okay.
Maybe like this.
Yes, that's how we're going to make it, but let's sort of. That's similar. Okay, so the very first thing we're going to do after we do this is we're going to figure out from the H2CO which one is the center atom, because everything's going to revolve around that center atom. So how do I determine the center atom?
The one with the most valence electrons?
The most metallic?
Most valence electrons, like
That's what
if it has, is that what you said?
Yeah.
Okay.
That's fine.
What's that?
Isn't it almost always carbon?
Right.
Almost, yeah.
Well, okay, so it's usually going to be the thing that wants to form multiple bonds. Let's go with that.
So it's,
And if I'm looking at two nonmetals, the one that's the most metallic.
Yeah.
Well, I'm going to give you a much better way to do this, and you'll see why this is. But for now, if I say I'm looking at, and by the way, can hydrogen ever be a center atom? Do I ever have to worry about that?
No.
No, why?
Because it only has
It only forms one bond, 2 electrons. Yes. So I'm looking really between carbon and oxygen. Which one is more metallic?
Carbon?
Carbon, right? Metallic, meaning going this way and down.
Right.
The opposite of electron negativity. Okay. And we'll figure out why that is in a little bit in this chapter. I doubt we'll get to it today because that's a newer topic that I might not want to introduce today.
So between
But
O and S will be
Between
S?
carbon and
no
oxygen,
SC.
the most metallic is carbon. That will be the center atom.
S.
Then I simply draw
S?
everything else around it
Yeah.
in a skeleton shape,
Yeah.
right? Symmetrically.
Yeah.
Go
Is
ahead.
carbon always the center?
Not necessarily. If
No,
I had
this
carbon
is-
and boron, which one would be the center?
Carbon.
Which one's more metallic?
Boron?
Boron.
Okay, so maybe
Oh,
not.
okay.
Boron.
So, but it will be a lot of the times.
If it's between O and S, then we'll pick S.
And we'll see, yes, more metallic would be S, and we'll see why that is, but we will have another way to determine it in a
Okay.
little bit. It will be
Okay.
based off formal charges.
Okay.
And we'll walk through what formal charges are and how to determine that, and that will give us the orientation of what's center. And almost always it will be the most metallic. I'm just making it easy and calling it most metallic at this point, because that's all we know at this point.
Yeah.
Now I fill in 1, 2, 3. So this how many electrons are in this? 2?
2,
2, so that's a total of
6.
6. So I had 12 to start, I just used 6, I have 6 left.
Yeah.
The next thing I do is I fill in these are called the terminal atoms, this is the center atom.
Yeah.
I fill in the terminals, this is already complete with
That's
2 electrons
complete.
each.
Yeah.
This one has only 2, so I say 2, 4, 6.
Done.
I filled in this terminal, so minus 6, I have 0 left. I can't now add any more to it.
Correct.
So now I must say, okay, well, is this the proper structure?
No.
My carbon is missing
You can make a
2.
double bond.
2 electrons. So then I could take 2 from any of these, fold them in,
Awesome.
And then they'll both be happy.
and
They'll both have their
We
cake.
share.
now
What
I
was
have
the-
this, I have a double bond, and now I have a complete Lewis structure.
What was the term of the parent? The parent structure or the parent?
That deals with the 3-dimensional shapes.
Yeah.
We haven't got, to get to the 3-dimensional shapes, chapter 10,
Mhm.
we have to do this first.
Yeah.
Okay.
Right, the 3-dimensional shapes are gonna be
I'm
based on this.
loving
This
this
would
class.
form three, right? Three
Right.
electron pair groups around it, because this counts as one, and
Yes.
therefore would be a trigonal planar,
Mhm.
and then we'll talk
You
more
like
about
this
that
at
later.
65, right?
Okay,
Right.
so is this okay?
That's great.
Everybody comfortable with that?
Now it's
Okay, cool.
Yeah.
Okay, so
Wasn't
this
born
is
with
just
that
doing the
knowledge.
same
No, my
thing,
mom fed it
and there we
to
go.
me like through her milk.
Okay, one other one I'll do here, this one has what?
Negative
so
charge.
that's-
A negative charge,
Mhm.
that's important. So what do I do when I have, that basically means it's an ion. What do I do with ions?
Add, you add in electrons in this case?
Okay, so, I'm glad you
Negative, you're
said this
actually
case.
taking away.
If I have a negative ion, or an anion,
Any.
that means that those are extra electrons that I include in my valence electrons when I make the structure.
Yes.
Correct.
If I have a cation or a positive one,
You
that
take
means I
away.
take away some of the valence electrons to fulfill my,
Of the charge.
structure.
Correct.
Okay. Okay. So with this one, how many valence electrons do I have here?
So you have 6 and then 7, you have 12, 13, 14,
14.
14, yes.
7 from the Cl, 6
the
from the
minus
oxygen,
charge.
6 and 7 is 13, plus 1 from the negative charge.
Right.
Even though I don't know why they're writing this, this is essentially just a 2-atom thing.
Right.
All right, there's no center atom here, I don't get it, but there's the 14, okay. Maybe they thought that same thing, let you finish this, this is just 2 atoms. The main
Just to,
thing is
like,
you have 14.
identify it, yeah.
Right.
The only part I care about here is that you identify what that negative charge represents in terms of the valence electrons.
Mhm.
Because I'm gonna give you something a little more challenging than this.
Would you bracket the structure, right?
And at the end, you want to bracket the structure
Yeah.
so that you make sure that you know, because the charge comes outside of the bracket
Yeah.
to indicate it's an ion. Okay, so here's another one. So this is a weird one. I actually gave you guys this one in 65, but I didn't ask you to do it. I gave you a structure and asked you if it was right or wrong, and then why. So how you could identify from a structure. Why is this one strange? What's different about this one?
2 center atoms.
2 center atoms.
Right.
Right,
Maybe
the
double
hydrogens
bond.
go around the nitrogens, you end up with the double bond between the
Double bond.
nitrogens. Each nitrogen itself is a center atom.
Correct.
Okay,
It's not hard.
yeah.
Maybe I should have taken.
Let me, I want to do one, so, let's see, let's try PO4 3 minus. Let's do this one. Let's just do this as something different that you don't have in your notes to make sure that if you're given one, you can solve it. How many valence electrons do I have here?
24.
That's
6 por 4, 24.
is it 32?
4 times 6, 24,
26?
plus 3, plus 5, right?
Yeah,
So what is that?
32.
Oh, I got it right.
I said, yeah.
Oh, yeah, you did.
That's why I started doing it, so that people,
Oh.
knew, because somebody already, you announced it, you announced the site.
I guessed it though.
I doubt that.
I know that.
I was like, I knew it was
You
like
can't
30
be that
something, so I
lucky.
just blurred out.
What's the center atom?
That would be P.
P. So in this case, it's easy. I'm not worried about what's more metallic because there's only one of them.
Yeah.
Right.
Okay. So P, and now I'm going to go O, O, O,
Oh,
O.
baby. Oh.
Now I'm going to fill in these. I just filled in 8, so 32 minus 8 leaves me with 24.
and then
Okay.
26.
So
Outer atoms.
lone pairs.
So now let's do this.
Well, divide it by 4. And we get
No,
2,
6.
4, 6.
Yeah.
2, 4, 6. 2,
If you
4,
divide it by
6.
4, then you know.
2, 4, 6.
And that is
Let me divide how I want.
How many is that?
24?
24.
You're done.
Now, in all fairness, it's actually a little different than this, but for the purpose of what we want to know, this is what we're going to do. So then I would bracket this like this. I would put 3 minus up
3
here,
minus, right.
and that's my Lewis structure.
What do you mean? I don't know?
If you don't bracket the thing, where would you
Why is he
put
saying it's
electrons?
different?
Those 3
In all fairness, it's different.
electrons
Because of the
at the
charge.
top. Where would you put that?
What
In
three?
the,
I mean, this,
yeah.
that's why you bracket it. That's the
Oh,
whole
you have
reason
to
for it.
bracket
I know the
Oh.
bracket,
Because you're
but
saying
he
this
said
whole
in all
thing
fairness, it's a
has a
little
3 minus charge.
Okay.
If I put it, if I took away the brackets, put it here, it looks like I'm saying they're connected to that oxygen. That's why the brackets are
Yeah.
there, is to identify that
When
this
you
is the 3 minus representing, it's within the structure that those 3 are there.
What is different? You said in all fairness, it's different.
What's that?
You said in all fairness, it's different. What's different?
Oh, I don't want to get into it.
Oh, okay.
This could be double bonded and all kinds of different stuff.
Oh, okay.
That's based
Oh,
on the
the
position
drawing.
of the
Yeah.
phosphate.
Right.
Yeah, yeah.
Okay. So that's the basic Lewis structure and development of it. Is that okay?
Yeah.
Okay, good. Okay, now, sometimes you could have more than one Lewis structure that's the same, that's valid. Okay, so I'm going to introduce it like this. If I take O3,
Yeah, tell me.
let's draw the Lewis structure for O3. How do I do that? How many valence electrons?
18.
18. DE equals 18.
What to tell you?
What's the center atom?
Oh.
Now I'm going to put 2 around it. Okay, we're good so far.
Yeah.
But which O do you put in the center? I'm just kidding.
So,
So just so you know, that's kind of interesting. I get that kind of question, believe it or not. That they're all chemically equivalent.
yeah.
For real?
So think about that, right? In this case, they're all oxygen. They're all chemically equivalent. There's nothing different about any of them from each other.
Okay.
Okay? And I'll fix this a little bit so you can see the nuances here. So what's the next thing I do?
Each one needs at least one.
Double bond? Oh,
1, 1.
uh-huh. Another?
Total 4. What do I have left?
14.
You got 16?
I have 14 left?
Sorry,
Or was this supposed to be 16?
No,
how
no,
many,
14.
How many are we supposed to have here? 6 times 3.
What happened? What?
Oh,
18.
3
We have
bonds.
18. 3.
Yeah.
So I just used 2 and 2, so I used 4, so 18 minus 4 is
Yeah.
14.
14.
I'm good. What?
Can't do that. Don't worry.
It's okay, don't worry about it. Just
Oh.
keep going. It's like basic additions.
Now, I fill in the terminal atoms.
Why?
So 2, 4, 6,
What don't you understand?
8,
No,
10,
this
12.
Part, this part.
Minus 12, what do I have left?
4. Oh, 2.
2.
2. Okay, this is now, what's wrong with this?
Can you double
The
bond it?
middle oxygen is in here.
You can double bond it.
You need
using
one.
that.
So I'm just asking what's wrong with it first.
The middle oxygen.
Oh, the
The
lump?
The middle
one is not
oxygen doesn't have an
satisfied.
octet around it. Let me
Yeah.
recall terms that I actually haven't brought up, right? So just assuming. So the middle one doesn't have it. So now, what can I do as a result of that?
Add extra
Double.
bond.
I can double bond it, right?
Yeah.
Okay. So I could drop these here. I can also do what? I could drop these here.
Right.
What's the difference? I told you the oxygens are chemically equivalent.
Right.
So let me show you something. I'm gonna do something here to clarify this. I'm just arbitrarily going to set up, and by the way, this is exactly what you do in OChem, right? You have one more semester of Gen Chem, then you're going to OChem, and you gotta fix things in carbons and these chains. I'm gonna arbitrarily call this oxygen 1, 2, 3, so I have a reference point
Okay.
of which one. It doesn't matter which one I call which, okay? Now, I'm gonna say, I'm gonna take oxygen 1, I'm gonna take 2 electrons, and I'm gonna fold them down so that I now have a double bond here, and what does that show? Is that a proper structure?
No.
Why? What's wrong with it?
Still- 'cause
I've
they have
used up
more
all
than
my
8
electrons. Everything has an octet around it.
I just want to-
What's wrong with it?
There's nothing wrong.
There's nothing wrong with it.
Yeah,
It's perfectly fine, right?
completely fine.
Nah, you have to distribute the electrons equally, no? Around the, never mind.
You can't.
I have to have octets around all this. I'm doing Lewis
You have
structures.
that?
Oh.
Yeah.
I have an octet around everything.
Yeah.
Gotcha. Yeah.
2, 4, 6, 8.
Yeah, that's right.
2, 4, 6, 8. 2, 4, 6, 8.
That's right.
Yeah,
Okay, now,
but
but I could also do this. This is right, by the way. But I could do this,
And triple bond them?
no.
and I'm gonna keep, this is still my 1, 2, 3 for my reference point.
You can
So we
just
know
make
that this is the
2
same
to
oxygen.
3 have the double bond instead of the 1.
And I could do this.
Yeah. I get what he's going.
Is that also right?
Yes.
Yes. These are called resonance structures.
We did that.
They're both the same structures that fit the Lewis structure.
Mhm.
Yeah, like-
There's nothing different between those.
And they exist in nature as the average of all the resonance structures?
And I'm gonna
Yeah.
get to that.
What the hell?
The first thing I want to point out is these are what I'm referencing as resonance structures. Another way to state that these are
You
valid
guys
structures
did that in 65, right?
for the same molecule. The second thing I'm going to say is a way to show this is just to put an arrow, double arrow, and that means they're both the same. I could have more than just 2. I could have 3 or 4,
Yeah.
whatever, depending. Usually you don't have more than 3
I've
different
seen
ones.
3, yeah.
And also this double arrow could be here and this could be moved over there, just so you know.
Actually, I should don't go to real lab.
We're going to talk about bond lengths. So I'll introduce that briefly now. A single bond is always longer than a double bond, which is always longer than a triple bond. The more bonding, the tighter you bring the atoms together, the nuclei together. Okay?
Correct.
In this case, if I were to check the bonding patterns of these, you would expect I'd get what? The bond length of O and O that was a double bond, and one that was a single bond, because it doesn't matter which one these would be.
Correct.
That's what you would expect I would get. But in reality, I don't get that. In real life, what I'm going to get is, I'm going to get, this is going to be shorter than this, so let's call this 10 picometer, and we'll call this one 7 picometer. Okay, just to get a sense of this, okay? This is going to be shorter, double bond, more pull closer together. So you'd expect I'd get maybe 50% 7 picometer, 50% 10 picometer. But what I really get is something like maybe 8.5 or 9 picometer for my bond lengths. Which means that I don't have this or this. I have a hybrid of it. Okay, so what I really have is this. Let me make sure we reference our 1, 2, and 3 oxygens. And I get something like this. I have the electron from this double bond or this one distributed equally between both areas. What I'm doing is I'm delocalizing the electron density. Here, it's localized here. If I use these 2 oxygens, it's localized here. If I could spread it out between both of those bonds, I delocalize it, which creates a more stable overall molecule. So you get a hybrid. So this is a fair representation here
But the
But this is equally fair and more representative of reality. You could show me either way on an exam, but I want you to understand that this is really what it comes out. And I know that because what I actually see, if I take the bond lengths of this, is something maybe like 8.7 picometer, which is not 7 or 10. It's in between. It's a hybrid. It doesn't have to be perfectly in between. That's why it's not 8.5 or whatever it would be exactly. It's going to be a little bit closer to one than the other, but that's because it's being distributed throughout both sides, not just one. So either representation is perfectly fine in discussing resonance structures.
Awesome.
Okay, that's what you're saying, basically? Okay. So, here's the example we just showed. Everything I just said, so it's a waste of time. There's the double arrow, okay, good. And here, okay, so here's their representation from the book of the hybrid. So you have this would be this one here. Let's do this. Let's call this structure 1 and structure 2. Okay. So now I have dog 1, dog 2. Okay. You actually don't have either dog. You end up with a hybrid between them, which is what this is representing. Right. This is their example here. And then they do the same thing here. How do they draw this? Good, they do the same thing with the dash lines here. The dash just means that you have both properties from both sides.
Awesome.
And the reason I labeled them 1, 2, and 3, by the way, is because you could simply say in 3D, I could take this out and just turn it, and you have the same if I don't label and show you the different oxygens as 1, 2, or 3. So orientating yourself on which oxygen you're referencing shows you that you have these two positions that are different. Otherwise, it'd all be the same oxygen because they're chemically equivalent.
Right.
If you just rotate it and it'll be.
Right. If I take this as rotated, don't have the 1, 2, 3, looks the same. Yeah. That wouldn't be a hybrid. That would be the same.
You know, yeah.
Okay. Okay. So. Okay. So the molecules delocalize everything. This structure here, by the way, the reason why. Okay. I should say, and I think I already said this, but let me just reiterate it. By having this and this here versus this actually, as I mentioned before, it delocalizes electrons. They're not all focused here or all focused there. They're now throughout the whole thing. So the density is now delocalized as opposed to localized. That's the concept. That on its own makes the molecule more stable, is the point. And that's all they're saying here. If it's more stable, that means its potential energy is
Greater.
lower. Lower. The lower the potential energy, the more stable the complex
I'm
is.
doing 6.
So by delocalizing the electrons like that,
Or do
you
7,
create a
6,
more
7
stable
is fine.
complex by reducing the potential energy.
It's
Just to keep
fine.
those terms all together.
Leave it on this side.
Is that okay?
Yep.
Okay, good.
Or leave.
And this says everything I just said, except for I did it with the pictures. Hopefully that helps. Same thing. Exactly. Why are they saying the same thing like multiple times? Okay.
In case I'm not gonna hear it the first 5.
Okay, here you can draw. Okay, so here they're giving you something different. This is a cation, NO2, positive, and they want you to draw the 3 resonance structures of this. So let's do that. So I can do this. I could do that. And I could do this. So these are considered all resonance structures. Why? Why are these considered resonance structures?
Because they're not symmetrical.
They all have the full onset for everything in every shape.
They all fit the Lewis structure. The atoms are all connected in the same way. I kind of want to point out a couple things here that you might have missed, some basic things. If I had OON, would that be a resonance structure of these 3?
No.
What is it?
No, OON. Let me make sure I'm clear on this. Because when you get to more complicated things, I want to make sure that you understand what you're looking at to make the determination. So OON, forget how they're connected, versus ONN, these cannot be resonance structures. They're connected differently.
Right.
Okay, this is where you have the same connections, different number of bonds at different places, but they all match a Lewis structure.
Okay.
Okay, so that's why these would be different resonance structures. See the ends in the center of each one.
I would have gotten that wrong.
So the position of the elements are important.
Oh, absolutely.
Yeah.
When you're talking
because
about
then that
resonance, yes,
changes
yes.
how
Mhm.
the structure. Once you have
I could write it a different way, but it wouldn't be a resonance structure of this, yes. If that, and it doesn't necessarily mean it's right. So then our objective is which one is right,
Right.
right? So that's what we're trying to figure out through these things. How do we determine what is right or what isn't right? What actually happens in reality? And in this case, when you have these different resonance structures, they all can exist appropriately if they fit the Lewis structure in nature. That's kind of the general point here. But maybe one of them exists a little bit more than the others. So maybe one of them's more stable. Or maybe I could determine why is this one more stable than this one.
Okay.
Because I could put together a Lewis structure that fits this if I could do one that fits that, right?
Mm-hmm.
And how would I make that determination of which one it actually is? Of course, I could take the bond lengths between N and O's versus O and O and O and
Okay.
N. And if I don't have anything like this, well, clearly that's not going to exist,
Right.
right? But if I have these three, are any of those more or less than the other one?
Sure.
Or do you just have all three of them?
All three, right?
And we're going to figure that out. This is where I'm leading you. This is where this lecture series is taking you.
Okay.
Isn't it like
Is-
all the different charges of each one has to balance out and give the charge of the overall molecule kind of thing?
So that's exactly where we're going with it, is figuring out something called a formal charge. And the formal charge at each position will look at and evaluate to determine the best structure, which is also always going to give you the center atom as the most metallic that I brought up earlier. And the point of this is because you're trying to figure out what actually exists in nature and why. So I got to have some rationale behind it, right? Just like I asked for you guys on an exam. You don't have to give me the right answer all the time, but you have to give me at least the right rationale, or at least some reasonable rationale. Because you never know in different scenarios. When I look in everything that I've covered so far, have I always talked about the upper half of this chart? I usually don't get too deep down, and now we're starting to go down a little bit into the D's. You notice how we've never touched the F's? Why is that?
Complicated.
Complicated, but why? What does that mean? That's true. It's more complicated. Exceptions. I start to find that all these things that fit in the upper half don't fit at the lower half. They start to change. There are variations in them. And there are reasons. We got to figure out why, though, right? You can't just say, okay, well, it's just different. Cool. Right? When you go to the store and you buy a candy bar, there are different candy bars. Why do you choose the one you choose? Because you like it more.
Right.
Right? Why do these things, molecules, form the way they form over other conformations? More stable. And more stable means they are less energy.
Right.
Less energy, that means they like it, right? They like to have less energy. That makes it more stable. The same way you like a particular candy bar. You've got to have a reason, rationale, and then you try to figure out what that rationale is, right? Something tastes good.
More
or
sweeter.
Maybe it has more sweet,
Right.
less sweet,
Or less sweet, right?
right? Has a better consistency, chewier, crispier,
Right.
whatever it is. These things are also trying to find a proper orientation, and we're trying to say, how do we figure that out? And as we get more and more involved into the periodic table, we'll find it gets more and more complicated. It's not so simple like we used the original with only a couple electron elements. Okay. So identify which structures are resonance structures here. Someone help me out.
Identify which of the following structures
What'd you say?
The A and D is this resonance?
You said what?
And A, D, and C?
A, B,
No, A, D, and C.
A, D, and C?
Right.
Yeah, AC.
So B is not 1. Why?
Because the
Oh, it's
center
connected to
is
two
different? The
nitrogens,
center is
whereas
different?
on the others-
The orientation of how they're connected,
Right.
right? I have O in the center here, I have N in the center of the other ones. Pretty straightforward.
Yeah.
Now, on an exam, do I want to look a little closer into that?
You're gonna make it harder.
Well, I want to make sure that these are proper Lewis structures,
Yeah.
right? So I might want to just make the Lewis structure and then double check and make sure that these are all Lewis structures. Right, because one of them may not match. Maybe one has more than an octet. Okay?
Stop laughing.
Okay, now I'll finish. This is good. This is about where I wanted to get to. Now we're going to get into formal charges. These are, this is going to tell us which structure is right in a lot of cases, okay? Especially, for example, here, it will tell us which structure is right out of these three, or at least which one's more common. Okay, let me see. I'll let you read that. I've already introduced what we're doing. I will say, okay, these are fictitious charges. The charges we're going to assign do not actually exist. It's just a way to, it's like a pseudo scheme. The same way we did oxidation states. Remember oxidation states,
Yeah,
right?
right,
That was, you don't actually have charges unless you have an ion.
exactly.
And then again though, what necessarily constitutes an ion,
Right.
right? That was that change in electron negativity. I just gave you a new chart.
Mhm.
You have a new criteria for ions.
Right.
So it
And
does vary.
activation numbers, right.
But now we're gonna look at formal charges which are not an actual assigned. They're gonna be based on what's being greater pulled towards it or whatever else. Okay. Okay, I'm gonna skip over that, and what I really want to do is, first let's define what a formal charge is. How to determine what a formal charge is, and you do need to know this, and I will ask you a question on the final, at least one related to this. Formal charge equals the number of valence electrons minus the non-bonding electrons plus 1/2 the bonded electrons. That's how you determine the formal charge of each atom, because you're going to figure out each atom in a compound what the formal charge is. Okay? So that means that valence electrons, let's take a look at bromine.
Yeah.
How many valence electrons does bromine have?
Bromine, 7.
7. So 7 goes here.
Okay.
If I have bromine connected to oxygen, how many bonds does that bromine form?
Oxygen?
Yes.
How many bonds? 1, 2, 3, 4?
What did you just say, one?
Oxygen, bromine.
3.
One.
Would I have some structure like this?
Yeah,
Okay.
so 2.
2 bonds.
Bromine is forming, one bromine is forming how many bonds here?
Oh, 1 bond.
One bond. So that's
Can you
1/2
listen?
the bonding electrons. How many electrons are in a bond?
2.
1/2 2 is what?
1.
1. How many non-bonded electrons?
6.
1, 2, 3,
6.
6.
6 plus 1 is what?
7.
7. 7 minus 7 is what?
0.
That's the formal charge of bromine in
Oh,
this
okay.
compound.
Nice.
And then I can figure out the formal charge of oxygen. What's the formal? So that's 0. So we know if this one's 0, what's this one?
0.
0. What's the formal charge of the oxygen?
6 minus 7, negative 1.
So let's go
Oh, you gotta do the whole thing again.
Yeah, the whole shebang.
6 minus, how many non-bonding electrons?
That'll be 4,
4. Minus 1/2, how many bonded?
2, 1.
2,
2.
4,
Uh-huh.
Wait, it's minus 1/2? I thought it was plus 1/2.
plus 1. Right? 6 minus 4 plus 2.
Oh,
6 minus 6,
0.
formal charge is 0.
gotcha.
That's how you determine the formal charge of each atom, and I'm going to put this together to why we're doing this.
Okay.
But this is how you determine the formal charge of each atom in a compound.
I don't get the 1/2 bonding electron. Like, where is that?
How many, is this a bond?
That's a bond.
How many electrons?
2.
2. Is this a bond?
Yeah.
How many electrons?
2.
How many total electrons are in these bonds?
4.
So 1/2 of 4 is what?
2.
That's the way to say it. Okay. So all I wanted to do first, I introduced why we're going to look into formal charges, what they're going to do for us. But I first also want to introduce now how to determine the formal charge. Now, after we determine the formal charges of different structures that fit Lewis structures, Now we'll figure out which structure is the best and most likely to be found in nature as a result of this. Okay, so do something here with the H. We already did the same thing. This is just H and fluorine, so you could look at this in your thing. You'll see 0 and 0. And,
Really?
okay, now,
I did
I
this.
have a structure. I have resonance
How am I
structures
gonna do the
and
rest?
different Lewis structures that all
In
fit.
between?
I then look at the sum of all the formal charges in a neutral molecule must be 0. Okay? So if the molecule is neutral, I could have -1 and +1, so the overall formal charge is still 0, or 0, 0, 0. Overall charge is 0. Okay. The sum of all formal charges in an ion must equal the charge of the ion. If it's a +1, that means it has to be +1 overall. Okay. These things are no big deal. Here's where you start determining the best structure. Okay. Small or 0 formal charges on individual atoms are better than larger ones. So this is better than if it was -1, -1, and +1.
You pick.
0, 0, 0, the lower the formal charge, the better the structure. If I have two different structures that are the same based on Lewis accounts, then I look to see if the formal charges, and wherever the formal charge is the lowest in magnitude, that's the best one. Does that make sense?
Yeah.
So formal charges are talking about the distribution of electrons around the.
Essentially, yeah.
Yeah. Okay.
Basically, yes.
Okay. So if it's evenly distributed, then that means it's good.
It's better.
Better.
Because it means it takes less energy to hold them together.
Right.
Okay. Now, the last one is when formal charges cannot be avoided. Then, ideally, the negative formal charges, in this case the -1, must reside on the most electron negative atom. Okay? So is oxygen or bromine more electron negative?
Oxygen.
Actually, it happens to be bromine, but we'd have to look at electron negativity chart. That was a tougher one. Let's say F and O. Let's say F and O. What's more electron negative? F. So the negative would have to be on the F. The positive would have to be on the O.
What last one? No.
Then I'd have to make sure that these were switched. So what would happen
What
is,
if we run out of
in the structure, however it comes out, I could make it come out different ways depending on the structure. So one structure might give me this, another one might give me this. Then I would take this
Honestly,
one
chapter
over
8,
this
you don't
one.
need it. You know it.
That's how I'm going to determine which structure is better.
Because oxygen.
We'll see. Because oxygen's more electron negative based on
And
this
so
right
you
now.
want it to be the negative or 0.
All I want is it to, first I'm looking at the lower one, the better, period.
Yes.
If I have where I have to use the formal charges, then the negative formal charge must be on the most electron negative atom. That's all I'm saying.
Okay.
Nothing more than that.
Got it.
Okay? So let's walk through and see what this means now. Okay. So I want to rather do one, but okay. Structure A, structure B, HCN, HNC. Both of these fit the Lewis structure. So I'm looking at this here and this here. They both fit the Lewis structure appropriately. They're all octets, everything works okay. So then I say, which structure is better? I use formal charges. So number of valence electrons here, number of non-bonding electrons, and half number of bonded electrons. Okay. And I go across. Then I figure out the formal charges of the H0, C0, N0. Over here the H is 0, over here the N is +1, and over here the C is -1.
So we want structure
A.
So we want structure A because it has the least formal charges, that is the most stable compound. Also, if you think about what we learned earlier, is N or C more metallic?
C.
You notice how it followed? This is why the most metallic is going to be the best structure, because it has the lowest formal charge. So this will be the structure that you actually get.
Okay.
That's how you would determine which one is the better structure and found in nature, even though you could write different ones. Okay. Okay, now we get to do an example. I have these three things here. Let's assign formal charges to each atom and then determine which one is the correct one. What's the formal charge on the oxygen?
Okay, so it's
6 minus
6.
7.
Mhm.
2, 2, 2, plus 1/2, 2. 2, 2, 2 is 6, plus 1 is 7.
7.
Yeah,
6 minus 7 minus 1.
Yep.
What about this one here?
carbon is gonna be
4 minus 1, 2, 3, 4. 4 minus 4 is 0. And 5 minus
2.
1,
2, 3, 4, 5.
Yeah.
5 minus 5 is 0.
Yeah.
Okay, minus 1, 0, 0.
So you have 6.
Theater, what's the next one? B, what's O? What's the formal charge on the oxygen here? 6 minus 4, 5, 6, 0. What's the charge on this one? 4 minus 1, 2, 3, 4.
Mhm.
0. What's the charge on this one? 5 minus 4, 5, 6. Minus 1.
Cool, cool.
I'm just, instead of saying half the bonded, I'm just saying 1 for the bonded.
Yeah, that's
That's
fair.
an easier way to maybe think about it.
Yeah, yeah,
Is that okay?
that's a lot better.
Okay. Cool. Let's do that. This one, 6 minus 2,
Uh-huh,
4, 1, 2, 3, so this is going to be plus 1.
right.
4 minus 4, 0. 5 minus 6, 7. Minus
Minus 2.
2, okay. Plus 1, okay. Now, the first thing I could say is which structure, based on rule number 3, is not a good one here?
See?
C. This has higher charges all over the place. Okay, so this one's eliminated. So between A and B now, rule 4, which one is the best structure?
B.
B.
And we say B because we want the negative on what? The most electron negative.
Yeah.
So is O or N more electron negative?
N.
Oh, the O is more electronegative.
Do you need to actually know, remember I mentioned earlier, you don't actually have to have the numbers, you need to know the pattern,
So, oh.
the trend. So which one is going to be more electron negative?
Oh.
The O.
Oh, so which structure is the best structure here?
A.
A.
That's it.
Okay.
Everybody see that?
Yes.
And in reality, if you look to see, you'll see that this one will be the most abundant by far. in terms of its structure. Okay. Does that make sense? Okay. Let's try another one. We have just enough time to finish off this. Draw the Lewis structure, including resonance structures. Okay, let's go ahead and take a look at those. So which structure is favored here? Do I need to worry about the hydrogens here?
No.
No. Okay. So I'm really looking at, do I need to worry about the carbon here too? That's pretty obvious. 4 minus 4 is 0.
Right.
4 valence electrons, and then 1, 2, 3, 4. 4 minus 4 is 0. 4 minus 4 is 0. So I'm looking at the nitrogen and the oxygens.
Right.
Those are the ones that are different in each one, potentially. So let's take a look. 6 minus 4, 5, 6, 0. 6 minus 7 minus 1. 5 minus 4
Mm,
plus 1.
Yeah.
Right?
Mm-hmm.
Okay. Over here,
4.
5 minus 4.
It's plus 1.
Okay. 6 minus 7.
Negative 1.
6 minus 6.
0. Oh, they use the inner one.
Okay. So we just left that 0 and that one 0 and changed the ones. Okay. So now which one would be the proper structure here?
They're both the same
Use
numbers.
a hybrid,
They're both identical.
because the oxygen, it's not like one oxygen is more electronegative than another oxygen.
Okay.
So I'd say that this would be when you use the hybrid.
Okay. So, what do you have to say, Peter? Go ahead.
No, never mind.
Would having the single bond to the oxygen with that -1 charge be different than the double bonded one?
This one here,
Yeah.
and then this one. So I
Yeah.
have -1, -1.
Oh, no, it's-
One
It's the same
connection,
thing,
one,
yeah.
double,
Alright.
double.
I take my glasses off.
No, that's good though. This
I was
is,
thinking-
I want you guys to think about these things. I want you to start identifying, seeing. I want you to work through this, and then on an exam, this should be much easier.
I don't get what we're doing. So what are we doing right now?
I think it would be the second one, just
Because of the position
of
where
the
the
height.
hydrogen.
Wouldn't it be
It's
easier to
so
argue that they're
close.
the same, right?
Yeah, they're the same.
That's what I was saying, but you didn't agree.
Oh,
I didn't agree or disagree, I didn't say anything.
You didn't disagree.
I'm
no?
just trying to
He
see
did
what
what
people,
you do to us.
I wanna see what people come up with. This, this would.
Maybe
this
second
would
guess.
form-
Question yourself.
What would this actually look like in a structure? If you were to draw this, what's the best way to put this?
Put both of those.
I'd have this distributed through both, right?
Mm-hmm.
And what would that do here?
Hybrid.
It'd create that hybrid. And that would change this -1, and this -1
To zero.
would be distributed throughout both, which is exactly where you delocalize. It's not localized charged up here, and the charge here isn't localized. I'm now delocalizing it by drawing this through.
-half each one.
Does that make sense?
Right.
So the actual structure would look like, not the double bond here, the double bond there, but the dashed line going throughout both.
It's like a previous. Hybrid.
Mhm.
Yeah.
Yes, absolutely. Is that okay?
Yeah.
And as a result of that, the overall formal charge then, you would think about would be much lower, because it wouldn't actually be -1 here or here, and this wouldn't actually be a +1 here or here, because the electron density is being shared throughout. Hence, the resonance structure is a hybrid of both, not just one or the other. Is that okay? Okay, with that, let's see, what do I have here? Okay, let's still more, let me see your notes. What comes up after this?
Oh, we're not there.
Examples and then exceptions to octet.
This is the last example.
I believe so.
Okay, I want to finish with this because I want to start fresh on Thursday. So this will be the last thing we'll talk about. Use formal charges to determine which structure shown here is better.
Okay.
So, do you have this in your notes yet? It's already solved?
Oh, no.
It's not solved.
Solve it, and then let's figure it out, and then we're done for today.
We're done for the day.
The lab is open at 7?
What's that?
The lab is
What
open
time
at
is
7?
The other lab.
6:50, I think. You have all the way till it's done, till the end of the class.
From
Tiny, tiny.
6:50
How long
till.
is the test gonna take?
Let's finish this problem. I'm worried about the S and the C here, basically. That's all I really need to worry about, right?
Yeah.
What's the S, how many valence electrons does S have?
S is 6.
6 minus how many here?
4,
4?
right?
6 minus 4?
Is 2.
1, 2, 3, 4.
2 plus?
That's 2 plus. C is 4
4 minus.
minus 6.
Right, -2
Negative 2. Over here, this should be easy. 4 minus 4.
is 0.
And 6 minus 6.
0.
What's the better structure?
Right.
Yes. How long did that take?
In your mind.
Right?
Right.
So we're looking at the second one here. This has the lowest formal charge. Oh, I don't have that in. This one should have the lowest formal charge.
Right.
And that's it. So this is the way the structure should look in nature. And this is why. Is that okay? Everybody get the concept here? Go ahead.
When simultaneous atoms are neutral, do we have to actually write in 0? Can we leave them blank and only put if it's a negative or positive, and just leave neutral charge of 0, or without the 0?
Okay, so it depends on what you're asked for. If you're just asked to determine which structure is best, you don't have to put those, no, if you could do it in your head. I would argue that you always want to put them so that you can compare and double check. Because it's easy on an exam when you're stressed out to have different things going on in your mind. And just not worrying about it, putting the 0, 0 there makes it easier for you to see that. But if you do that just in your head, and then you do this and you say, oh, this is better, then you can circle it. It usually will ask an explanation though, and then you want to explain it. If you already have the zeros up, you could just simply say less formal charge. Right, with the indicator. So it depends on how it's asked and what's being asked, but yeah, if it's just saying which one's the better structure, then yeah. Okay. Okay, with that, for those of you who took the exam, I'll see you Thursday. For those of you who are going to take it, good luck. It really was not made to be that hard. I would say this is probably one of the easiest exams that I've given this semester. So,
Get over
you
it.
know,
Is it in the lab?
it's in the lab. So go to the lab and Andrew will proctor it.
I need to run one real quick. How long do we have until? What is the last?
What time does the second lab close?
I think it's less than 10, I think.
And closes at 10? Yeah. You have
Okay.
till 10.
Thank you.
Okay, see you guys.
Professor, do you let us record your lectures?
Yes, do it.
Do you let us post them online?
No.
Don't really care.
How do you know?
Oh, really?
You can if you want.
Yeah, he said he
I don't
doesn't
see-
care.
I don't see why you want to, but you can.
Well, because other students have requested your lectures.
Yeah,
And then we
but I
want
change every time. How situations change on how people interpret who's here, how many, you know, when I'm downstairs in a 101 and I have 71 students, I have more to deal with there, so I'll change up. How I feel, I mean, literally, I'll give examples.